Welcome! In this video, we'll explore vectors in 2 dimensions. By the end of our session, you will be able to first identify and describe the key characteristics of a vector. Second, perform operations with vectors, like addition and scalar multiplication, and calculate the dot product. And third, determine the direction of a vector, its magnitude, and the angle between 2 vectors. These skills are fundamental for understanding physics, computer graphics, and many other fields. Let's get started. Our first objective is to understand what a vector is. We'll identify its key characteristics. At its most basic, a vector is a quantity with both a magnitude and a direction. Unlike a scalar, which only has a size, a vector tells you how much and in what direction. For example, your speed is a scalar. It might be 50 miles per hour. Your velocity, however, is a vector. It's 50 miles per hour north. Geometrically, we can represent a vector as a directed line segment. This means it's a line segment with an arrow at one end. The arrow points in the direction of the vector. The point where the vector begins is called the tail, and the point where it ends, where the arrow is called the head. Now for magnitude. The magnitude of a vector is simply its length. It's the distance from the tail to the head. This length represents the size or strength of the vector. Now let's see how we can place a vector in a 2-dimensional coordinate plane using its starting and ending points. Suppose we have 2 points, P1 and P2. We can define a vector that starts at P1 and ends at P2. This vector is denoted with an arrow over the letters P1, P2. To describe this vector using components, we find the change in the x-coordinate and the change in the y-coordinate. These are called the components of the vector. The horizontal component, A, is the change in x, which is the final x minus the initial x. That's x2 minus x1. The vertical component, b, is the change in y, which is y2 minus y1. So, the components tell us how to move from the tail to the head, a units horizontally and b units vertically. Let's work through an example. Suppose our starting point p1 is at minus 2, 1, and our ending point p2 is at 4, 3. To find the vector p1, p2, we calculate the components. The horizontal component a is 4 minus negative 2, which equals 6. The vertical component b is 3 minus 1, which equals 2. So, our vector is less than 6. This vector describes the movement from p1 to p2. A special case is the zero vector. If the starting and ending points are the same, p1 equals p2, then both components a and b are 0. The vector less than 0, 0 is called the zero vector. We've learned to find a vector's components from 2 points. Now, let's explore 2 powerful ways to represent a vector, geometrically from the origin and using unit vectors. The components of a vector, for example, the vector with entries a and b, are incredibly useful because they allow us to standardize its position. Any vector can be visualized with its tail at the origin, 0, 0, and its head at the point a, b. This is a key concept. A vector is not tied to a single position. A vector representing a displacement of right 6, up 2 is the same vector, no matter where it starts. So, our vector, with entries 6 and 2, can be represented as an arrow from the origin to the point 6, 2. This standard position makes it easy to understand and compare vectors. This gives us a very clear geometric meaning for the components. There's also a very convenient way to write vectors using what are called standard unit vectors. As we discussed, a unit vector is a vector with a magnitude of 1. The standard unit vector I points along the positive x-axis. Its components are open angle bracket 1, 0 close angle bracket. And the standard unit vector j points along the positive y-axis. Its components are open angle bracket 0, 1 close angle bracket. These 2 vectors form a basis, meaning we can express any other 2D vector as a combination of I and j. For a vector with components open angle bracket AB close angle bracket, we can write it as A times the vector I plus B times the vector j. Let's apply this to our previous example. We found that the vector P1, P2 had components open angle bracket 6, 2 close angle bracket. So, in standard unit vector notation, we would write it as 6i plus 2j. This notation is very common in physics and engineering, so you should be comfortable moving between the component form open angle bracket AB close angle bracket and the unit vector form AI plus BJ. We've talked about direction, and we've talked about magnitude. Let's make sure we can find the magnitude for any vector. The magnitude of a vector is its length. For a vector with components less than AB, we can find its magnitude by using the Pythagorean theorem. If you visualize the vector from the origin to the point AB, you can see that it forms the hypotenuse of a right-angled triangle. The legs of the triangle are the horizontal component A and the vertical component B. Therefore, the magnitude of the vector, denoted with vertical bars, is the square root of the sum of the squares of its components. That is, the square root of a squared plus b squared. Let's find the magnitude of the vector from our first example. Our vector was less than 6, 2. Its magnitude is the square root of 6 squared plus 2 squared, which is the square root of 36 plus 4, or the square root of 40. And finally, let's talk about finding the direction of the vector. Using basic trigonometry, we can find the angle theta, which is the angle the vector makes with the positive x-axis. In our right triangle, the side opposite the angle is b, and the side adjacent is a, so the tangent of the angle is b by a. To find the angle, we take the inverse tangent of the ratio of the vertical to the horizontal component. It's crucial to consider which quadrant the point AB lies in to ensure you get the correct angle. For our vector less than 6, 2, the point 6, 2 is in the first quadrant. So, the angle is the inverse tangent of 2 divided by 6, which is approximately 18.4 degrees. Now we'll move on to our second learning objective, performing operations with vectors. Let's start with scalar multiplication. Scalar multiplication is when you multiply a vector by a real number, or scalar. The result is a new vector. The components of the new vector are found by multiplying the scalar by each component of the original vector. The scalar c distributes to both a and b. Visually, scalar multiplication changes the magnitude and, potentially, the direction of the vector. If the scalar is positive, the new vector is in the same direction but is c times longer. If the scalar is negative, the new vector points in the opposite direction, and its length is the absolute value of c times the original length. Let's use our vector v equals less than 6, 2. If we multiply it by the scalar 1/2, the resulting vector is less than 3, 1. This new vector is half as long as the original and points in the same direction. Notice that the new vector is parallel to the original vector, just scaled up or down. Next, let's look at vector addition. To add two vectors, v1 and v2, we simply add their corresponding components. So, the x component of the sum is the sum of the x components, and the y component of the sum is the sum of the y components. Geometrically, there are two ways to visualize this. The first is the triangle law of addition. To add vector v2 to vector v1, you place the tail of v2 at the head of v1. The resultant vector, their sum, is the vector that goes from the tail of v1 to the head of v2. It represents the total displacement if you first follow v1 and then follow v2. The second method is the parallelogram law. If you place the tails of two vectors at the same point and complete the parallelogram they form, the diagonal starting at that point is their sum. Notice this is geometrically equivalent to the triangle law. Let's work through an example using components. Let v1 be the vector 1, 3, and v2 be 2, negative 4. Their sum, v1 plus v2, is 1 plus 2, 3 minus 4, which is the vector 3, negative 1. And of course, vector subtraction is just a special case of addition. To subtract v2 from v1, you add v1 to the scalar multiple of negative 1 times v2. In other words, v1 minus v2 equals v1 plus negative v2. Our final vector operation is the dot product. This is a very powerful tool because it results in a single number, a scalar, and tells us something about the relationship between two vectors. The dot product, sometimes called the scalar product, is calculated by summing the products of the corresponding components. So, the dot product of a1b1 and a2b2 is a 1 times a 2 plus b1 times b2. Let's see this in action. Using our vectors v1 equals less than 1, 3, and v2 equals less than 2, minus 4, their dot product is 1 times 2 plus 3 times negative 4, which is 2 minus 12, or negative 10. The fact that the result is negative tells us something which we'll explore in a moment. But first, let's look at a special case. What happens if we take the dot product of a vector with itself? For a vector less than AB, the dot product with itself is a squared plus b squared. Notice that this is exactly the magnitude squared of the vector. So v dot v equals the magnitude of v squared. We've seen the algebraic definition of the dot product. Now let's explore its geometric interpretation, which is what makes it so powerful. The dot product of two vectors is equal to the product of their magnitudes multiplied by the cosine of the angle between them. This is often called the geometric dot product. This formula connects the algebraic calculation to the geometry of the vectors. Let's use this to find the angle between our two vectors from the last example, v1 equals less than 1, 3, and v2 equals less than 2, minus 4. We know their dot product is minus 10. We also need their magnitudes. The magnitude of v1 is the square root of 10, and the magnitude of v2 is the square root of 20. Plugging these values into our formula, we get minus 10 equals the square root of 10 times the square root of 20 times the cosine of theta. The square root of 200 simplifies to 10 root 2. Dividing both sides by 10 root 2 gives us cosine of theta equals negative 1 over root 2. The angle whose cosine is negative 1 over root 2 is 135 degrees. So our two vectors are obtuse to each other. The dot product's geometric formula gives us a very useful condition for determining if two vectors are perpendicular. Two vectors are perpendicular, or orthogonal, if and only if their dot product is 0. Why is this true? Well, if two non-zero vectors are perpendicular, the angle theta between them is 90 degrees. The cosine of 90 degrees is 0. Since the dot product is the product of their magnitudes and the cosine of the angle, the dot product must also be 0. Let's test this with two vectors. Let v1 be vector 4, 2, and v2 be vector negative 1, 2. If we take their dot product, we get 4 times negative 1 plus 2 times 2, which equals negative 4 plus 4, or 0. Because their dot product is 0, we know for sure that these two vectors are perpendicular. This is a very common application of the dot product. Finally, I want to briefly mention how the laws of sines and cosines can be used with vectors. When you add two vectors, say u and v, to get a resultant vector w, those three vectors form the sides of a triangle. The vectors u, v, and their sum, u plus v, can be arranged to form a triangle, either in the parallelogram or triangle method of addition. This triangle follows all the rules of geometry. This means you can use the law of cosines to find the magnitude of the resultant vector or an angle in the triangle, as long as you know enough information. Similarly, if you know two angles and a side, you can use the law of sines to find other sides. For example, if you know the magnitudes of two vectors and the angle between their tails, which would be gamma in this triangle, you can find the magnitude of their sum using the law of cosines. This shows how our understanding of trigonometry connects directly to vector algebra. This skill is particularly useful in applied problems in physics and engineering. Let's quickly review what we've covered today. We started by identifying the characteristics of a vector. A vector has both magnitude and direction. We learned how to write a vector using its components, less than a, b, or in standard unit vector form, ai plus bj, and how to find its magnitude, v, and direction angle, theta. Next, we learned how to perform vector operations. We saw how to multiply a vector by a scalar, add two vectors by adding their components, and calculate the dot product v1.v2 equals a1a2 plus b1b2. Finally, we used these tools to determine angles. We derived the cosine formula v1.v2 equals the product of their magnitudes times the cosine of the angle between them, which led to the powerful conclusion that two non-zero vectors are perpendicular if and only if their dot product is 0. We also saw that you can use the law of cosines on the triangle formed by vector addition. You now have a solid foundation for understanding and manipulating vectors. Keep practicing these concepts, as they are essential in many areas of mathematics and science. Thank you for watching.